Hello everyone, my name is Akira Sone. I'm a postdoc from Los Alamos National Lab. Today I'm going to talk about our recent work on defining the heat and the work and quantum charges equality in open quantum systems. This is a joint work with Yishan Liu and Paolo Capararo from MIT. Let us first review how to define the work in closed quantum systems. The conventional approach is to take so-called two-time measurement scheme. We first prepare this initial state to be the Gibbs state and take the first measurement of the initial Hamiltonian on the system. Then the wave function collapses into a certain eigenstate of the initial Hamiltonian with a certain probability. Then we change the Hamiltonian. In the closed quantum systems, the eigenstate is evolved under the unitary operation, and at time t, we measure the system with the final Hamiltonian. Then again, the wave function collapses into a certain eigenstate of the final Hamiltonian with a certain probability. Since there is no interaction between the system and the path, the work along the trajectory n to m is just the internal energy difference. Then averaging the exponentiated work over all the nonequilibrium processes, we can obtain the following standard charges equality, which shows the relation between the nonequilibrium work and the equilibrium free energy difference defined by the initial and the final Hamiltonian. From Jensen's inequality, we can obtain second law of thermodynamics. This has been verified in different quantum systems such as trapped ion and NMR system. Then it is natural to ask, how do we define work and heat in open quantum systems? Actually, this is the open problem. First, there is no observable for work and heat. The other reason is that with two-time measurement scheme, the second measurement will destroy the correlation between the system and the path. Thus, we do not have information about the path. Heat is information about the path. And as we can also see from the first law of thermodynamics, by measuring the system only, we cannot distinguish heat and the work. Also, as Defner, Phys, and Zurek pointed out in their PRE paper in 2016, with two-time measurement scheme, in general, the formalism does not take into account the information caused by the back action due to the second measurement, which would change the state of the system. Thus, two-time measurement scheme is thermodynamically inconsistent. As a solution to these challenges, we take one-time measurement scheme, which was first introduced by Defner, Phys, and Zurek in 2016 for closed quantum systems. The differences between this scheme and conventional two-time measurement scheme is they get rid of the second measurement. We assume that we do not perform the final measurement, but still estimate the energy difference along a certain realization trajectory from the expectation value of the final Hamiltonian with respect to evolved eigenstate obtained from the first measurement. In our scenario, we consider a general open quantum system dynamics. We consider a general quantum process which can be described by the superoperator, which could be the unital or non-unital. We assume that the initial state of the composite state system is the coupled Gibbs states, which means that we start from the case where the bath and system equilibrate at the same temperature. Second, Hamiltonian of the bath is time independent. Third, we consider the case that we do not have any access to the bath but can only measure the system alone. Following the same approach of Defner, Phys, and Zurek, we define the internal energy difference as the differences between the expectation value of the final Hamiltonian with respect to the evolved eigenstate and the first measurement result. By following Defner, Phys, and Zurek for a closed quantum system, we take the following distribution of the internal energy difference, which is a good choice because we can get exact average internal energy difference. Then we derive the following charges equality. The first term is a standard charges equality with respect to the system only. In the second term, tau st tensor tau b is the uncorrelated Gibbs states defined by the final system Hamiltonian and bath Hamiltonian. For theta sb, this is a thermostate, actually, which is maximizing the entropy of the total system subject to the following conditions. 1, we fix the average energy given by the final Hamiltonian of the system alone. Here, since we cannot measure the energy of the bath in practice, so we guess the final energy of the system is fixed. Second, theta SB is constructed by evolving from the post-measurement state of the initial projection measurement. And third, since we do not know the temperature of the final state, we guess that the temperature does not change. Then we can derive theta SB, which we call the best guess thermal state, which is well defined. But please note that this is just a guess state, which is not the exact final state. D is the relative entropy between the guess state and uncorrelated Gibbs state. Let us take a look at the third term. What is enthalpy? This is the state of the bath after time t as if the true time evolution of the total system gives the guess state from its initial state. So we call this process as guess process. Then we can find that the exponent describes the energy dissipation of the bath as if the true time evolution of the total system is a guessed process. So we call this quantity QB as guessed heat because it is derived from the best guess state. Please note that since the best guess state is well defined, so this guessed heat is also a well-defined quantity. As we can see, by only considering the measurement only on the system only, we can obtain a well-defined heat-like quantity. So we have guessed heat here, and from the first law of the thermodynamics, we can obtain a work-like quantity, which we call guessed work, because this quantity is also derived from the best guess state. And please note that this quantity is also well-defined. In this way, by taking advantage of one-time measurement scheme, by only considering the accessibility to the system only, we can obtain a well-defined and new notion of work and heat. Then we derive the following modified Jaginski equality with respect to this guessed work, and by using Jensen equality and the monotonicity of the quantum relative entropy, we can obtain the following maximal work principle with respect to the guessed work. We can also recover the result of Defner-Pazin's rec for closed quantum system because in the closed quantum system, the guessed work is simply the energy differences of the system, which is the exact work. So we indeed obtain a bound for the principle of the maximal guessed work that importantly only requires the knowledge of the system state only. Avoiding measurements on the path is essential, as this bound describes the maximal usable and extractable energy the system can provide, which is of relevance of experiments and practical applications. Actually, the guessed work has very important meaning in terms of quantum hypothesis testing. Please recall that we have this guessed process. Since the best guess state is constructed by considering the time evolution of the post-measurement state of the system by initial measurement, it is a quantum process. The second line actually corresponds to the classical isothermal process. Actually, the quantum relative entropy between these two final states contributes as the scaling of the quantum hypothesis testing. This is come from the quantum stance lemma. Given n IID copies of these two final states, we can define two probabilities, type 1 and type 2. Type 2 probability is the probability that says while the true state is the uncorrelated Gibbs state, which you can obtain from the classical process, our POVM measurement indicates that the state is the best guess state, which we can obtain from the guessed quantum process. Then, the natural log of the minimum of the type 2 probability asymptotically is related to the quantum relative entropy between these two states. Then, from the Jaginski equality with respect to guessed work that we derived, we can find that the guessed work asymptotically is related to the minimum type 2 probability. Therefore, the operational meaning of the guessed work is a scaling of the quantum hypothesis testing involving the classical isothermal process. So in conclusion, we introduced a new notion of the work and heat from the one-time measurement scheme only on the system alone for the open quantum systems. And we derived a modified quantum Jaginski equality and second law of the thermodynamics with respect to introduced notion of the work and relate them to the quantum hypothesis testing involving the classical isothermal process. And we also generalize the result of Defner's. Thank you very much for your attention.